and a thin layer of gold. The device became commercially useful in photographic light meters in the 1930s. 28. Point contact microwave detector rectifiers made of lead sulfide were used by Jagadish Chandra Bose in 1904. The cat's whisker detector using natural galena or other materials became a common device in the development of radio. However, it was somewhat unpredictable in operation and required manual adjustment for best performance. In 1906, H.J. Round observed light emission when electric current passed through silicon carbide crystals, the principle behind the light-emitting diode. Oleg Luzev observed similar light emission. Tom. In the years preceding World War II, infrared detection and communications device.
I did click by mistake, so we have to read page by page. That happened because I'm close to fall asleep because it's so hot in my apartment.
Carl Ferdinand Braun developed the crystal detector, the first semiconductor device, in 1874. Metallic sulfides, although this effect had been discovered much earlier by Peter Munkaff Rosenskjold, SV, writing for the Annalen der Physik und Chemie in 1835. 28, and Arthur Schuster found that a copper oxide layer on wires has rectification properties that ceases when the wires are clean. William Grills Adams and Richard Evans Day observed the photovoltaic effect in selenium in 1876. 29, a unified explanation of these phenomena requires a theory of solid-state physics, which developed greatly in the first half of the 20th century. In 1878, Edwin Herbert Hall demonstrated the deflection of flowing charge carriers by an applied magnetic field, the Hall effect. The discovery of the electron by J.J. Thomson in 1897 prompted theories of electron-based conduction in solids. Carl Baedeker, by observing a Hall effect with the reverse sign to date in metals, theorized that copper iodide had positive charge carriers. Johann Cohen Eichsberger classified solid materials like metals, insulators, and variable conductors in 1914, although his student Joseph Weiss already introduced the term Halbleiter, a semiconductor in modern meaning, in his PhD thesis in 1910. 31. Felix Bloch published a theory of the movement of electrons through atomic lattices in 1928. In 1930, B. Gooden stated that conductivity in semiconductors was due to minor concentrations of impurities. By 1931, the band theory of conduction had been established by Allen Hayes Wilson and the concept of band gaps had been developed. Walter H. Schottky and Neville Francis Mark developed models of the potential barrier and of the characteristics of ametal semiconductor junction. By 1938, Boris Davidoff had developed a theory of the copper oxide rectifier, identifying the effect of the p-n junction and the importance of minority carriers and surface estates. 28. Agreement between theoretical predictions, based on developing quantum mechanics, and experimental results was sometimes poor. This was later explained by John Bardeen as due to the extreme structure-sensitive behavior of semiconductors, whose properties change dramatically based on tiny amounts of impurities. 28. Commercially pure materials of the 1920s containing varying proportions of trace contaminants produced differing experimental results. This spurred the development of improved material refining techniques, culminating in modern semiconductor refineries producing materials with parts per trillion purity. Devices using semiconductors were at first constructed based on empirical knowledge before semiconductor theory provided a guide to the construction of more capable and reliable devices. Alexander Graham Bell used the light-sensitive property of selenium to transmit sound over a beam of light in 1880. A working solar cell, of low efficiency, was constructed by Charles Fritz in 1883, using a metal plate coated with selenium and a thin layer of gold. The device became commercially useful in photographic light meters in the 1930s. 28. Point contact microwave detector rectifiers made of lead sulfide were used by Jagadish Chandra Bose in 1904. The cat's whisker detector using natural galena or other materials became a common device in the development of radio. However, it was somewhat unpredictable in operation and required manual adjustment for best performance. In 1906, H.J. Round observed light emission when electric current passed through silicon carbide crystals, the principle behind the light-emitting diode. Oleg Luzev observed similar light emission in 1922, but at the time the effect had no practical use. Power rectifiers, using copper oxide and selenium, were developed in the 1920s and became commercially important as an alternative to vacuum tube rectifiers. 29. 28. The first semiconductor devices used galena, including German physicist Ferdinand Braun's crystal detector in 1874 and Bengali physicist Jagadish Chandra Bose's radio crystal detector in 1901. 32. 33. In the years preceding World War II, infrared detection and communications devices prompted research in lead sulfide and lead cyanide materials. These devices were used for detecting ships and aircraft, for infrared rangefinders, and for voice communication systems. The point contact crystal detector became vital for microwave radio systems since available vacuum tube devices could not serve as detectors above about 4000 MHz. Advanced radar systems relied on the fast response of crystal detectors. Considerable research and development of silicon materials occurred during the war to develop detectors of consistent quality. 28. Early transistors. John Bardeen, William Shockley and Walter Brattain developed the bipolar point contact transistor in 1947. Detector and power rectifiers could not amplify a signal. Many efforts were made to develop a solid-state amplifier and were successful in developing a device called the point contact transistor which could amplify 20 dB or more. 34. In 1922, Oleg Luzev developed two-terminal, negative resistance amplifiers for radio, but he perished in the siege of Leningrad after successful completion. In 1926, Julius Edgar Lilienfeld patented a device resembling a field effect transistor, but it was not practical. R. Hilsk and R. W. Pohl in 1938 demonstrated a solid-state amplifier using a structure resembling the control grid of a vacuum tube. Although the device displayed power gain, it had a cutoff frequency of 1 cycle per second, too low for any practical applications, but an effective application of the available theory. 28. At Bell Labs, William Shockley and Holden started investigating solid-state amplifiers in 1938. The first p-n junction in silicon was observed by Russell Ole about 1941 when a specimen was found to be light-sensitive, with a sharp boundary between p-type impurity at one end and n-type at the other. A slice cut from the specimen at the p-n boundary developed a voltage when exposed to light. The first working transistor was a point contact transistor invented by John Bardeen, Walter Hauser Brattain, and William Shockley at Bell Labs in 1947. Shockley had earlier theorized a field effect amplifier made from germanium and silicon, but he failed to build such a working device, before eventually using germanium to invent the point contact transistor. 35. In France, during the war, Herbert Matter had observed amplification between adjacent point contacts on a germanium base. After the war, Matter's group announced their transistor amplifier only shortly after Bell Labs announced the transistor. In 1954, Physical chemist Morris Tannenbaum fabricated the first silicon junction transistor at Bell Labs. 36. However, early junction transistors were relatively bulky devices that were difficult to manufacture on a mass production basis, which limited them to a number of specialized applications. 37. See also. Defnium. Semiconductor device fabrication. Semiconductor industry. Semiconductor characterization techniques. Transistor count. References.
Yes, we not read that. So that was 51 minutes. But let's stop the video to save the power. That was last dated 16 July. It's 8 p.m. or 6 p.m. evening. So probably I have to add this to my read again list about my on the central processing units. I have a read again list somewhere. Let's do that. So we have to read this again in the future. But I have other semiconductors goods. But let's save on the power on the camcorder because it's only 6 p.m. So let's close it. And next is wafer. It's 6 p.m. and it's super hot. It feels much more hot today than the other days. So, and it's still 30 degrees. So let's save on the power. I'll go charge my camcorder, then I will upload.